Welcome back. In section 4.1.2, we'll be talking about sigma notation. In the previous problem, we saw that to get good approximation for the area of a region, we'll be adding the area of many small rectangles. So we did 4 here, but really we're after a million rectangles. So there's no way we'll be adding these by hand one at a time. So in this section, we will introduce a new notation to make these big summations manageable. All right, so definition 4.1.1, this is what I want to define. All right, so I'll tell you what each of the pieces are, and then we'll spell it out. All right, so first of all, this symbol here is Greek letter sigma. So sigma is an S and it stands for summation. And then we'll be adding the AK. So AK, those are the terms to add. And we'll let K vary. So K will be what we call the index of summation. This is a variable. We'll call it the index of summation. Some people like I. I don't really like it because I find it gets lost and I like K better, but if you see I, it's the same idea. And then I'm going to have K0 and N. So that tells you that K should go from K0 to N. So this is the starting value for K, and the N is the N value. So in this case, I would start with K equals K0, and then I would keep adding terms until I reach AN, and then I stop. Okay, so it's just notation. All right, so let's try an example, example 4.1.2. I want to expand the following summation. So the first one I have is this sum right here. My variable is K as usual. It tells me to start at 3. So my first term will be for K equals 3. And then I'm going to keep increasing it until I reach the N value, which is 6. 6. All right, K equals 4. I'll have a term for K equals 5. I'll have a term for K equals 6, which will be my last one. All right, so for each of these values of K, you evaluate this, and that's what we'll add. So here it's 2 times 3 plus 5. And the next term, K, is now 4, so it'd be 2 times 4 plus 5, 2 times 5 plus 5, and 2 times 6 plus 5. All right, and I'm going to add it all. All right, so what I'll end up with is 2 times 6 plus 5, 11, 13, 10, 15, and 17. That's what I'm adding. And if I actually tally it up, which I've done, you get 56. All right. So this tells you to add all of those and it would give you 56. All right. Let's try a second one. All right. So I'm starting at 1 and I'm going to N. So K equals, the 5, sorry. K equals 2, K equals 3, K equals 4, and K equals 5. I'll get 3 on 1, 3 on 2, 3 on 3, 3 on 4, 3 on 5. All right, and that's it. K from 1 to 5, I have 3 on K. We would just ask to expense. We don't actually have to tally it. Just to complete the problem, let me tell you that's 137 over 20. All right, I think you got the point. Let's try one more. I'm starting at 2 and I'm going all the way to 4. So not too far. I have 2, I have 3, and I have 4 to do. Notice that I have a second variable here. I have n. N doesn't take any value. I don't have a summation for n, so n will just stay. So my denominator will have an n in it, and that's just it. All right, and then I'm going to plug in k equals 2, so I'm going to get 8. I'm going to get 3 times 4, that's 12, and 4 times 4, that's 16. All right, and if I tally it up, I'm going to get, I'm sorry, the number I got made no sense. Let's tally it, 20, 36. Oh, I see. I had 56, just a little typo. All right, so you can see, I mean, it's really just notation. It doesn't have much mathematical meaning. It's just a way of writing a big summation. I mean, these are not so big, but we'll make them bigger. Big summation in a short amount of space. All right, so let's play with these a bit. We'll need to be comfortable with them enough. And so let's do a few extra properties just to see. So to evaluate our approximation of area, we will use the following two propositions. They would tell us how to simplify and evaluate certain sums so that we can actually evaluate big sums of area of rectangles. All right, so if I have a sum with as a term a sum of two things, then I will be able to split it. I can add all the A's first, then add all the B's second. All right, and second property that I want, if all of my terms have a constant C that doesn't depend on K in it, then I can pull that constant out of the sum, but it cannot have any K's in it. All right, the K's are prisoners of the sum, but any constant that doesn't have a K, I'll be able to pull it out. All right, so let me show you why that works. All right, so for the first one, I'll be adding all of these terms, up to n. Well, this is just a bunch of sums. I can order them as I wish. So I'm going to take all the A's and put them in front. So I will get AK0, AK0 plus 1, AN, and then I'm going to have the B's afterwards. So this first sum is the sum of AK, and the second one is the sum of BK. All right, let's do the same for the next one. So I do get the sum of the AKs plus the sum of the BKs. That's something we will use a lot. Now, if I spell this one, I will get C of AK0 plus C of AK0 plus 1 plus C of AN. And now I have C in every single one, so I can factor it out. Sorry. And what I have left here, that's the sum of the AKs again. So the C is now outside of the sum. Sorry. K equals K0, AK. All right, so this will allow us to split up complicated sum into sums of nice small functions of K. Right? And the second proposition will tell us how to evaluate these nice small functions of K. So if you add up from K equals 1 to K equals n, just the constant 1, you're going to get n. If you add up from K equals 1 to n, the constant K, so that will be 1 plus 2 plus 3, blah, blah, that's going to be n times n plus 1 divided by 2. If you sum K squared from 1 to n, you're going to get n, n plus 1, 2n plus 1 divided by 6. And if you sum k cubes, you're going to get, strangely enough, I'm getting exactly the square of what we had here. That's a nice way of remembering it. I mean, it's not a nice way of proving it. There's no clear way of seeing that this is the square of that one without some insight. All right, so I want to show you why the first one and the second one are true. If we have time later and if you care, I can show you this one, but I don't think it's as nice as these two. And we won't have time right now. Maybe towards the end when we start doing series, that will make sense. All right, so I want to add 1. So let me add 1 and then 1. And all the terms are 1, and I have, well, from 1 to n, I have n terms. And so I'm getting n. That's it. All right, so this one is very, very simple. All right, now the next one is more interesting. So let me call this sum s. Now s, if I spell it out, will be 1 plus 2 plus 3 all the way to n. I'm going to write this bigger, and you'll see why. So I'm going to write 1 plus 2 plus 3, and then n minus 2, n minus 1, plus n. At this point, you're thinking she's just using more space than she needs. But what I'll do now is I'll flip it. I'm going to start here. 1, 2, 3. If I add them in the opposite order, I'm still going to get s. And now I'm going to add the 2. I'm going to add this and this. So on the left, I will get s plus s, which is 2s. And now let's look at what happens here. So I get n plus 1. I get n plus 1. Here I get n minus 1 plus 2. That's still n plus 1. I'll get n minus 2 plus 3. That's n plus 1. And in fact, every single one of these terms will give you n plus 1. So that means that 2s I have 1, 2, 3, n terms. So I'm going to get n times n plus 1, which means that s is n times n plus 1 over 2. That's what we wanted. All right, there are rumors that this was invented by a mathematician called Gauss, a really famous mathematician, when he was really, really young. I mean, not sure what age is the last rumor, but it keeps changing. I'm not sure whether that story is true, but it's simple enough to potentially have come out of a young person's mind. All right, so let's try to use it. I have two problems here. I want to compute the following sum. So I have sum from k equals 1 to n of 3k squared minus 2k. So what I'm going to do first is I'm going to use my first proposition, this one, to split it up, to take the constants out until I have some of these sums here for which I have a formula. All right, so let's first split it up. And then I'm going to take the constants out using what we had for C. All right. Now from the last proposition, we have a formula for this, and we just proved the formula for this. In fact, it's still on the screen, so let me put it down here. So minus 2, this one was n times n plus 1 divided by 2. And the sum of k squared, it's right here. It's n times n plus 1 times 2n plus 1 over 6. So 3 times n times n plus 1 times 2n plus 1 divided by 6. And so let me just simplify this a bit. I have n times n plus 1 common to both. So I'm going to get n times n plus 1. And then here I have 3, well, actually, let me cancel 3 with the 6. So I have 1/2 of 2n plus 1. And then on that side, I would just get 2 over 2, which is 1. So if I divide by 2 here, I get n plus 1/2 minus 1. So I get n times n plus 1 times n minus a half. All right, so we went from a complicated sum with no one knows how many terms. It depends on n. And we got a pretty nice formula for it. So I would rather evaluate this any day compared to this. In fact, let's do it. Let's say that I have this sum from 1 to k, from k equals 1 to 45 of 3k squared minus 2k. That's exactly what we had in A. So it's going to be 45 times 46 times 45 minus a half. And so that would be much shorter to compute than the original one was. So 45 times 46 times 44.5, that's 92,115. That's it. All right, so now that we have the notation from summation down, we're ready to try to make the approximation of regions using rectangles more systematic. We'll have a sum of all these rectangles and we'll have a formula for it. We'll have a recipe. That's our goal in the next video. All right, thank you.